Okay. So I'm starting YouTube. I'm starting recording now. Welcome everybody to this new web lecture from the Instituto de Astrofísica Andalucía in Granada in Spain. Today is the first one of this new year after the holidays, after vacations, and Julián Alvarado Gómez will give us a nice talk. So thank you, Julián, for accepting this invitation for the first talk. And he will talk about stellar magnetism and extrasolar space weather. And Julián is from the Leibniz Institute for Astrophysics in Boston. So Julián will be properly introduced by Isabel Marquez. Please, Isabel.
Hello, René. Hello, everybody. Thank you very much for being here. It's a challenge to give a talk on the 1st of September, as we all know in Spain, since August mostly doesn't exist. But I mean, it's a good news for us to have Julián Alvarado Gómez giving us a talk today as a part of the Severo Ochoa program. And so it's a pleasure for me to first to thank Julián for having accepted our invitation to give this talk, and so it's a pleasure and an honor, and I'll extend this invitation for a participation of the colloquium. I mean, the meeting we are organizing in October to gather mainly all our Weblogia participants from the Severo Ochoa program. So you are kindly invited as well, Julián, to come here to be with us. Julián Alvarado Gómez is the 2019 recipient of the Carl Schwarzschild Fellowship at the Leibniz Institute for Astrophysics in Potsdam. And before this, he carried out a postdoctoral stance at the Center for Astrophysics, the CFA, the Harvard-Smithsonian in the United States. And before that, he started studying Bachelor Physics and then the Master in Astrophysics at the Universidad Nacional de Colombia and the Observatorio Astronómico Nacional. His doctoral studies then were carried out at ESO, the European Southern Observatory in Garching, near Munich, as part of the International Max Planck Research School on Astrophysics. His research interests include solar stellar magnetism and activity, and space weather for the sun and also for exoplanets, including stellar winds, flares, and coronal mass ejections, energetic particle events, etc., and on others, and star-planet interactions as well. And today, as René said, he's talking about stellar magnetism and extrasolar space weather. So I say again, thank you very much for being here, and the floor is yours.
All right. Thank you very much, Isabel and Miguel and René and everyone. And thank you again for attending this presentation. I'm going to share right now my screen. I hope everyone is seeing it right now. It should be.
Yes.
Yeah. Okay.
Yes.
Okay, perfect. And again, thanks to the organizers for this kind invitation to be part of this colloquium. I'm going to be telling you a little bit about the work I've been carrying out since over the course of my PhD and some of my work as a postdoctoral fellow and a Carl Schwarzschild Fellow here at the Leibniz Institute for Astrophysics in Potsdam. So the motivation for this work is a little bit on the fact that we want to understand the effects from magnetism, stellar magnetic fields, on the environment that is surrounding the star. And this includes the high energy emission, coronal structure and their stellar winds, how this affect planetary conditions, also time transient phenomena, energetic phenomena like flares, coronal mass ejections, and energetic particle events, and all the way to the outskirts of the solar and stellar system in this big sphere of influence, which is called the heliosphere in the case of the sun, but when we call them astrospheres in the case of stars. Basically, where the material from the stars, the solar wind and the stellar wind collides with the local interstellar medium. In order to do this, we perform a combination of observational techniques with detailed numerical simulations. So I'm going to be telling you a little bit about those in this talk. Part of the motivation is, of course, coming up from the exoplanet community because of the so-called concept of the habitable zone, trying to understand which conditions around other types of stars, which are not the sun, you could have planets that could perhaps sustain their atmospheres and perhaps sustain liquid water, with its eventual link to the generation of life or the existence of life. So what I have here is a diagram showing stellar mass against distance, orbital distance. We have the solar system on top. I'm sorry, I think I lost the pointer again. 1 second. Can I do this again? Yes. So we have here the solar system, and of course we have some lower mass stars, and this shaded region is in principle the region in which if you would take the Earth and place it there, the Earth would have a similar temperature at the surface. So in principle, you could sustain liquid water having the same atmospheric pressure. This is important. What you see here is that because of the distribution of stars in the Milky Way, that the large majority of stars are very low mass stars, K and M type stars, we really need to take into account these low mass star regimes here, like the one that we see in Gliese, 8581, Proxima Centauri, and the very famous TRAPPIST-1 system. But be aware that this is a log scale, so this habitable zone gets very closer and closer to the star as we go lower and lower in mass. So this is going to be important for what we're going to be discussing later. So the first thing I'm going to tell you today is a little bit about how we detect and map stellar magnetic fields. But when I talk about magnetic fields and astrophysics, I need to refer to the Zeeman effect and spectropolarimetry, and the solar physicists in the audience are probably experts on this. The first measurement came from the solar community, measuring the Zeeman splitting above a sunspot, basically demonstrated that this was actually a magnetic phenomenon. This was in 1908 by George Shirley Hale. What's important to remember from your quantum physics lectures is that the splitting of these lines is going to be a function of a number here. There's a quantity here, which is called the lambda factor of the effective lambda factor of the line, which is related with some properties of the orbital of the energy level, the strength of the magnetic field, and the wavelength of the light that you're looking. But this is a lambda square dependency. So you can see immediately that going to longer wavelengths is going to be better for trying to detect this line splitting. So another thing that is good to remind ourselves is that the Zeeman effect also introduces a particular type of polarization to the light, which is going to depend on the geometry of the magnetic field and the position of the observer. So a schematic view of this is shown here. Basically, you have a transition line when there is no magnetic field, and when you turn on the magnetic field, you generate this typical triplet of Zeeman splitting with different components, one with less energy and another one with a little bit more energy. But when you look at that from a geometrical perspective, depending on where the observer is located, these different components, the sigma and the pi components, will carry different types of polarization. So if you're looking from the line of sight, you're going to be seeing two components with circularly polarized light, basically in different orientations. While if you look from the perpendicular direction, you're going to be seeing linear polarization in these components. So the bottom line from this is that, in principle, if you can measure the splitting and the polarization of the light, you can, in principle, recover the vector properties of B. And this is basically the whole game of what people try to do. How is it done, for instance, in the sun? So I'm just going to refer here to one famous instrument, the heliosysmic and magnetic imager, which is on board of the Solar Dynamics Observatory. And that instrument uses this particular spectral line, an iron line in the visible range, which has a relatively high magnetization, or a lambda factor of 2.5. And basically, the line is extremely well characterized by all these filters here over which different Stokes parameters. This is a way in which we quantify the polarization of light, is measured across the entire line profile. And then a spectral inversion code is used to invert these profiles and determine the magnetic field on the surface of the sun. This is a cross simplification of all the work that is going behind it. But at the end of the day, what you get is maps of the surface magnetic field, which in the solar community are called magnetograms. And we can see one here in all its glory, basically showing all this beautiful structure that we have of the sun. That is basically limited basically by our spatial resolution, but we have excellent cadence here. Like you can have even images every 45 seconds or so. So On stars, the situation is much more complicated. I will first start with what kind of observatories we have for this. So, and for doing this, you will need high resolution spectropolarimetry. So I would say that across 90% of the results out there in the literature come from these three instruments. Narval at the at the Bernard-Lyot telescope in France, Espadons at the CFHT in Hawaii, and the polarimetric mode of the HARPS spectrograph at the ISO 3.6 meters in La Silla. Of course, these two are located in the north, so basically we observe the northern sky, and only HARPS right now is the one that has access to the southern sky. You see here the diameters of the telescopes and some properties of the spectrum, like the spectral resolution and the wavelength coverage. So if we look again at this equation that I showed you before, but we do some transformation with the units, we can put it in a more usable quantities that we typically associate with high resolution spectropolarimetry. So, and that is basically transforming it to the Doppler shift motions. So one interesting thing here is that, for instance, if you do the math for this equation and you try to calculate what would be the displacement through magnetic fields to a kilogauss magnetic field and a wavelength of, let's say, 500 nanometers with a typical lambda factor of 1.2, you will reach a displacement in velocity that is going to be below 1 kilometer per second. So this is really low. If you move the same magnetic field and the same lambda factor to 2 microns, this increases to almost 4 kilometers per second. So of course, you will in principle would like to try to do this the more to the furthest wavelength as you can. However, for the typical values of the involved quantities, even like the the lambda factor and the magnetic field strength, this displacement is below the sensitivity. So what can we do? So the solution that has been applied since the 90s, 1997 or so, maybe a little bit before, is applying a multi-line technique, which is typically the one that is mostly used is least square deconvolution. That the main idea is basically try to add the polarization signal throughout the entire spectral range. So basically what I show you in the solar case is that they have a single line that's extremely well characterized and you have all the signal to noise in the world. But for stars, what we have is going to be tens of thousands of lines. So the idea is to add the polarization of all of them, or as much of them as we can, to increase our signal to noise. And this is effectively what is done. Don't mind the equations here. This is just for the different Stokes parameters, how this is put into some sort of equation mode. But the important here, for instance, is that you can see here that we are taking into account the lambda factor of each line, the wavelength, and the depth, because of course, it's the line. If the line is more intense, then it's going to be contributing more. Some assumptions that are done is that a self-similarity is assumed. Basically, we assume that the Zeeman pattern that we're seeing in a line is going to be similar across all the lines, because of course we are dealing with an unresolved object, which is a point source like a star. And we're scaling by depth, raised wavelengths, and lambda factors, as basically the Zeeman splitting equation goes. In matrix form, this can be written like this. So you have an observed spectrum, you have a theoretical line mass. So this is supposed to be all the lines that you're supposed to see in the spectrum. And you will have a mean profile, and this is the convolution of those. The idea of this method is try to extract the mean profile for a given line mask and for a given observed spectrum. This is what you are aiming for. And this is why it's called a least squares, because it becomes a least squares problem. So at the bottom line is that you will take a full HL spectrum with 10,000s of lines, both in Stokes I or intensity, or Stokes B, like circular polarized light, and you will co-add all the lines following this recipe, and you will convolve them into a single line profile with a single Stokes signature. You will gain a signal to noise ratio on which is going to be proportional to the square root of the number of lines that you use. So it's going to be easier to do it for stars that are cooler because they have more spectral lines. And you're going to be reaching polarimetric sensitivities down to 10 to the minus 5 compared to a continuum level of 1, which is extremely good. In some cases, this is not feasible in all cases. So with this, then we can move to the part that we try to map the magnetic field. And for this technique that is called Zeeman Doppler imaging is used. In a single sentence, Zeeman Doppler imaging is a tomographic inversion technique that tries to recover a distribution of the magnetic field from a time series of polarized radiation, and which are going to be modulated by rotation. So this sounds very complicated, but it's just basically observe the star as the star is rotating and taking different snapshots of the distribution of the magnetic field, basically of the polarized light, and use that information to decompose that into a 2D distribution of what was the magnetic field that was generating the Stokes spectra that I observed. So in principle, it can recover the large-scale magnetic field structure because this, as we have unresolved observations and typically work with circular polarized light, a lot of the small-scale structure is going to be canceling out. So we typically only get like a blurred vision of what the magnetic field of the star as a whole looks like. So this animation kind of illustrates a couple of the principles behind it. For instance, of course, the longitudinal information is going to be given by the phase coverage. So the more you observe the stars rotate, you're going to have a better longitudinal resolution, let's say. The latitude of information is going to be coming from the velocity distribution. So if you have a line profile for your star and it has a spot that is located close to the pole, the Doppler motion of that spot is going to be restricted to very low velocities. So you're only going to see distortions close to zero velocity, to the rest frame of the star. But if the spot is located to the equator, it's going to have a much larger distortion over the course of the line profile. So in principle, this difference can allow us to locate in latitude. And the interesting thing is that because the magnetic field has these interesting properties with the orientation that I tried to explain at the beginning, we can have, for instance, for a case of a completely radial field, you will have a Stokes signature that basically only grows in size as it moves out of view, but it basically remains with the same sign. However, if the field is azimuthal or parallel to the surface, you will see that the signature is larger close to the limb and then changes sign and then becomes larger again. So in principle, with these differences, we can also disentangle what type of geometry the magnetic field of the star has. So I'm showing you here some examples, and when you do this kind of work, you kind of have to get a bit used to the cartography that people use in this. So for instance, people like to present this in maps like Mercator plots, like what you're seeing here, latitude against rotational phase or longitude, basically. And the tick marks that you see on the top is basically when, over the course of the stellar rotation, the star was observed. And the field is decomposed into the radial, the azimuthal, and the meridional component. This is for the star, which is psi A. These are the stellar properties here. Another example here, this is for a different perspective. It's basically called a polar flattened projection, in which you are looking over the pole of the star, which is located in the center of the image, and these concentric rings correspond to 30 degrees latitude variation. So you have here the equator of the star is this black line, and you will be seeing basically one hemisphere of the star and a little bit of the lower hemisphere. And again, the field is decomposed into the radial, the azimuthal, and the meridional field. This is for an M-type star, WX UMA, and you have the parameters here. But notice how strong the magnetic field is here. We're reaching values that approach a few kilogauss in magnitude. So we have done some of that mapping ourselves. So basically, I'm showing you a few examples of this Zeeman Doppler imaging reconstruction for these different sun-like stars, or from G and K type star. Basically, you see all the Stokes profiles that were observed, different rotational phases. This is the Epsilon Eridania famous star. And you can see here, for instance, when the observations are not very good, you have relatively low signal to noise. The amount of details that you can retrieve in your reconstruction is severely diminished. So you see these observations have much worse signal to noise ratio compared to these ones, have less phase coverage. So the amount of details is going to be a strong function of how many observations you have and how good the data or the data quality is. So with that, then we have been able to construct what is kind of the landscape of how the large-scale magnetism in full sequence looks like. And this is a famous plot in the community, which is actually called the confusiogram plot, because it has so much stuff on it and basically confuses everyone. But it's not so complicated at the end of the day. You have simply mass against rotation period of the star, and the simple sizes just represent how strong the magnetic field is. So you see the sun here, which overall, if you just basically don't think about the active regions, but basically the sun as a whole is not a very strong magnetic field. It's basically a few Gauss in magnitude, which is actually the smallest symbol in this diagram. If you keep the mass fixed, you will go to more rapidly rotating stars, And as soon as you do that, you will start to see that those symbols start to become bigger. And this means that the magnetic field in those objects is growing in magnitude. So you have here a very fast rotator, Abidor, around half a day rotation period, has a much stronger magnetic field than the sun. And if you look at the color is telling you a little bit about the geometry of the magnetic field. If it's red, it's mostly poloidal, so connecting one pole to another. But if it's towards blue, you will have more toroidal contributions, so fields that are wrapping around some of the rotation axis of the star. This dashed line here corresponds to the theoretical limit for the fully convective M stars, which are all the ones that are here in the bottom. Here's a famous example like Proxima Centauri, which is right here. The shapes of the symbols are telling you a little bit about the axis symmetry or non-axis symmetry of the field. So if it's a more round shape, it's going to be axis symmetric. If it's more like a star shape, it's a non-axis symmetric field. So this is more or less the panorama, how things look like. And you can see immediately that these low mass stars, with the majority of stars of the Milky Way, remember the connection with exoplanets, these stars have very strong, very intense magnetic field, typically poloidal, typically axis symmetric. However, there are some exceptions. All right, so, and this is already something I mentioned, this is what we have right now, but basically, currently there are new instruments, upgrades that are all coming up, like all of them are basically observing now some refurbishment of Norval. Espirou has taken over from Espadons, is doing a lot more work on M-dwarfs. We have the Pepsi spectrograph, from which the AIT has a good participation, which actually built the polarimeter, is 8 meters class polarimeter in an 8-meter class telescope, sorry. And we also now we have much more recently CRIOS Plus, which has been upgraded to have a polarization, polarimetric capabilities in one of the B units of the BLT. So in principle, now we are expanding a little bit. There's in principle access to more facilities to actually go to fainter objects and try to do similar work on them. So I'm going to be telling you here a little bit about some long-term variability quickly, because of course, this diagram doesn't involve one important parameter, is time. And time is, of course, something we know because magnetic fields are not static, right? If you look at the sun, you can see that, for instance, in all its glory, this type of diagram, this is called the butterfly diagram, the magnetic butterfly diagram of the sun, which is actually showing the magnetic cycle of the sun, basically, where you see the polarity flips and reverses back to the original one over a time scale of 22 years or so. Of course, if we look at different snapshots, we will see various changes in the magnetic field structure. And of course, these changes are going to carry over changes over the entire heliosphere and, of course, all the planets embedded within it. So for stars, of course, since a long time ago, since the Mount-Wilson HNK project, people were trying to measure this type of activity cycles on our star using things like chromospheric activity, like what I'm showing you here, the seminal paper by Sally Valiunas and collaborators, basically measuring the emission of the calcium HNK cores, which are basically in principle associated with vacuolar regions, in contrast with what you observe, a region which is basically just quiet zone. However, I would like to point out that only 5 of these systems, we have some sort of a coronal X-ray counterpart for these activity cycles, because when in the sun, when you look at the activity cycle of the sun, is very prominent in X-rays and extreme ultraviolet wavelengths, much more prominent than in calcium. So in stars, the situation is very difficult in the sense that we only have 5 stars in which we have done this in X-rays, and 3 of those systems are binaries. So this might complicate things a bit. And this is where I want to introduce this system, the iotarology, which is a G0 main sequence star, 600 million years old and rotating in a 7.7 days rotation period, which is basically the target of the Far Beyond the Sun campaign. This is an observational campaign. This is a comparison between the calcium HNK evolution of the star against long-term monitoring done with XMM Newton. And the interesting thing about the system is that this is the star with the shortest X-ray coronal activity cycle that we know of, which is on the order of 1.6 years. In the sun, this takes on the order of 11 years. So we decided to do a very intense polarimetric campaign on this, trying to map the entire magnetic field of the star over 18 different Zeeman Doppler imaging epochs. We follow it up with XMM Newton for 6 consecutive years, and we even observe it a little bit with HST to try to detect a stellar wind. I'm not going to be able to talk about all of this today. I'm just going to show you a little bit of some of the results from the magnetic field campaign. So basically, this is the first map that we retrieved, and you're seeing here again this Mercator projection latitude against longitude of the radial magnetic field of the star, and this dashed line here is the visibility limit, because the star has a 60 degrees inclination. So there's part of the star that is not accessible through observations. But of course, we have been following up for a long time, and you can see the evolution of the magnetic field as time progresses, and you can actually see by eye how the polarity of the magnetic field flips and returns to its original state. So I'm going to show it here in all its glory. Basically, here, all the evolution of the radial magnetic field, and you can see here how the magnetic field of this other star is changing. With this information, we were able to actually construct the first ever stellar magnetic butterfly diagram, which is actually very cool. This is the first diagram of its kind. So you can actually see a little bit of where the polarity of the magnetic field is taking place. Some of this, in principle, you can, it's up to interpretation, but a little bit of this movement of the large scale field towards the pole, where the cancellation occurs and the new cycle begins. And of course, this is all happening in a much faster time scale that we have on the sun. So I have here actually the evolution of this cycle over the course of these 3 years in the radial magnetic field and the azimuthal magnetic field, and how actually it might actually compares a little bit with what we know on the sun, again, for the radial and the azimuthal field. And this is in principle very interesting, because the main idea behind this campaign was to actually provide more data for our understanding of the dynamo models and the magnetic field generation on the sun and other stars. Right. So now that we know a little bit how we can actually try to observe and map the magnetic fields of stars that are not the sun, but other types of stars, we can try to study the space weather in those systems. And for this, we're going to be moving a little bit into the modeling regime. And for this, the work that I've been carrying out has been using the so-called space weather modeling framework, which is a collection of physics-based models that was developed by the University of Michigan, and is actually used to simulate the space weather of the solar system. The space weather modeling framework has a lot of systems and subsystems, or all these different modules that can be coupled together, and they receive inputs from observations in different ways, either constraints or boundary conditions, or some sort of, they basically inform some of the different models and the couplers. In this type of data-driven numerical simulations, this is, of course, a state-of-the-art 3D EBHT code, and it has been validated in multiple studies in the heliophysics domain. And this is very important, because we of course, we are going to be sending it to start, but we first want to have some sort of control of what all these models are doing, if they are able to reproduce the sun or not, or where they might be failing, and so on and so forth. So what I'm showing you here is one of the results of one of these validation studies. What you're seeing here is a comparison of the extreme ultraviolet emission simulated by the model in different wavelengths, channels of the stereo A satellite that observes the sun, and how it compares with real observations, which are actually in the bottom panel. So as you can see here, the model to observation match is extremely good. So this is very good, so that we can have some sort of ground truth, or some sort of nice reference to compare our stellar simulations to. This is, of course, high performance computing, and we have used it in multiple clusters across the US and Europe, and basically calculate self-consistently the coronal heating and the stellar wind acceleration, assuming that it comes out of alpha wave turbulence dissipation. We include radiating cooling, electron heat conduction, multiple other effects are included there. Some of the inputs from the code are actually requires the magnetic field on the surface of the star, which in the case of the sun is typically given by the Carrington rotation maps. But we can also use our Zeeman Doppler imaging maps, because they basically are based on the same principle. And we can model the corona, the stellar winds, the environment itself, star-planet interactions, and so forth. We've done a lot of this modeling work ourselves, trying to convince ourselves of trying to put the sun a little bit more on the context of stars, so degrading artificially the resolution of the sun, simulating its X-ray corona as it changes from solar minimum to maximum, simulating the solar wind structure, where you can actually see this textbook picture of the solar wind structure, in which you have fast wind coming out over the poles, slow wind generating this ballerina skirt around the heliospheric current sheet, and how the situation evolves when you have a much more complicated magnetic field in solar maximum, where the density of the wind increases, where the speed decreases, there's not so much wind, fast wind coming up, but you have much more complicated stellar wind structure. So with this, we have tried to start investigating the space weather of other systems. And I'm going to start with a little bit chronological order here. We did some study with Cecilia Garrafo from the Center for Astrophysics on the TRAPPIST-1 system. This is, of course, a very famous star. an M8 star with 7 planets in relatively very packed in orbits. 3 of them, in principle, might be located in this classical temperature-based habitable zone. And this is basically just an infographic about it, comparing it with the sun. Here's the orbital period in log scale in days. We have the solar system here, TRAPPIST-1, and how it's kind of a little bit of a larger mass analog to the Jupiter Galilean moon system, right? So some of these 3 planets here in principle are located in the so-called habitable zone, and are very interesting for the exoplanet community. They have really their eyes on them, looking for atmospheric signatures and trying to characterize them as much as they can. So what we try to do, unfortunately, as I said, we require a Zeeman Doppler imaging map to get everything started, but unfortunately, TRAPPIST-1 is extremely faint. It's something like 17 magnitude or so in visible wavelengths. So unfortunately, there is no Zeeman Doppler imaging map available. So what we did was basically took the magnetic field of a proxy star, which is GJ3220, which has a relatively close spectral type, similar rotation period, which in principle is one of the most important parameters. And we use that one instead to simulate the wind. This is, of course, a big approximation at the moment, but as soon as we have measurements of the magnetic field of the star, we should be able to do maybe a little bit of a better work on this. So we simulate the wind, and what I'm showing you here is different plots for the plasma density and velocity of the wind. All the lines here correspond to the orbits of the 7 known planets, and this white shaded region here is the so-called alpine surface of the stellar wind. This is a very important structure that is used to characterize the winds from the sun and star, and it's basically telling you where the outflows of the star become decoupled magnetically from the star and actually escape to form the wind. This is basically all the material that is actually moving out. Inside the alpine surface, we expect a very distinct and different plasma environment and different types of the star-planet interactions. This is something that we don't observe in the solar system because all the planets in the solar system are beyond the alpine surface of the solar wind, which is in principle located on the order of 7 to 10 solar radii or so. Actually, Parker Solar Probe is probably going to be providing us better constraint in that. So depending on the magnetic field of the star, maybe 4 or 6 planets might be completely embedded in the subalbenic domain of the stellar wind, which actually is going to imply that they will experience a very different type of stellar wind exoplanet interactions that we kind of observe here on our solar system. It's going to be more comparable to some of the things we actually observe on Jupiter, on the Jupiter-Io interaction, for instance. So we also did some work for Proxima Cen-C. Actually, we did Proxima Cen-D, but I'm just going to talk about Proxima Cen-C, which actually is a super Earth that is located much further out in the system, so 1.44 astronomical units. And actually, this is one of the challenges from this work, because in order to do this, at the time we did the study, there was no information again for the magnetic field of this object. The problem with this object is it's really faint for spectropolarimetry and for detecting the magnetic fields in a consistent way. And also the rotation periods. Proxima orbits has a rotation period of 83 days or so. So this is very hard to follow the rotation of the star for very long. So what we did instead, we used the output from a dynamo-driven a dynamo model for a fully convective star that was tailored to Proxima Centauri. This is work performed by Rakesh Yadav from Harvard. And we took the output from this simulation to perform the most comprehensive numerical simulation of this system to date. So we start from basically the stellar surface, very close to the star, the solar corona and the stellar wind acceleration domain, where basically the planet B lives, which is this line here. And actually this one, at the time of this publication, this was still a tentative inner planet, but now this planet has been confirmed by new observations. So this is another planet that is located even closer than Proxima B. And then we actually extend the simulation domain to really far out, more than 4,000 stellar radii box to actually encompass this orbit of 1.44 units, which is located here. And after that, we actually couple another model to drive a global magnetosphere model for this super Earth, making some assumption from the ionosphere and try to calculate what, for instance, what is the contribution from the stellar wind into process like the Joule heating of the energetic particles that have been deposited into this ionosphere. So if you, there are a couple of press releases out of this work, and this has been published in Astrophysical Journal Letters. So if you're interested, you can check it out. So after this, and to finalize this talk, I'm going to be moving on to some of the work that I've been doing, trying to understand a little bit better coronal mass ejections in active stars. So for here, I'm going to start a little bit from the beginning. I'm just making sure that we are on the same page. Just remember that whenever we talk about flares and coronal mass ejections, they are not the same thing. So flares are a sudden energy release that is basically manifested in radiation across the entire electromagnetic spectrum, while a coronal mass ejection is in principle, localized release of plasma and magnetic field into the stellar wind. So flares are basically light and coronal mass ejections are plasma. However, when you look at the solar statistics, the big flares are typically accompanied by a coronal mass ejection. So the larger the flare, the higher the probability is that this flare also comes with a coronal mass ejection. And the probability is really high, it's on the order of 90% or so, maybe even higher sometimes. So this poses the question, so okay, but what happens in more active stars? Because more active stars not only have more frequent flares than the sun, but those flares are orders of magnitude more energetic. So do they have also this type of CME activity that we observe on the sun? And this question has been basically posed by people in the past. So I'm taking here a couple of diagrams from this study of Jeremy Drake and collaborators in 2015, basically who explore the consequences of extrapolating the solar relations from coronal mass ejection mass and kinetic energy as a function of the flare energy, and to get to the activity levels that we observe in active stars. This is precisely what I'm seeing. What I'm showing you here, this is mass and kinetic energy as a function of the X-ray fluence of the X-ray energy of the associated flare for the sun. And these lines correspond to fits to some of the bins in which this data has been arranged, basically. So this calculation basically would yield that if you take this activity, these relations, and you extend it to the activity levels of active stars, you will reach some consequences for the amount of mass the star is losing in terms of CME activity, and the amount of kinetic energy is required to sustain that type of CME activity. These two numbers, 5 10 to the minus 10 and 10% of the volumetric luminosity, are extremely problematic for our understanding of how stars evolve and the amount of mass they lose. So I don't have the time to go into the details, but these two results are basically problematic and inconsistent to what we know about the winds from cool main sequence stars. So the conclusion from this study is that these two relations, the mass and energy relations from the sun, cannot be extended to stars, and they have to flatten out. They have to, there's something must be happening in order for them to not cause some sort of problematic in terms of these parameters. So we explore a possible solution for this, and this solution is the so-called suppression of coronal mass ejections by an overlying magnetic field. And this idea actually comes from the sun, as many ideas in stellar physics, which in some cases, like for instance, this particular active region, which is a famous one, you have active regions that generate a lot of flare activity. Like here, this active region generated more than 30 M-class flares, 6 X-class flares, but only one of these flares, actually a minor one, generated a coronal mass ejection. All the others were only flares, but no CME. This is the so-called flare-rich CME poor active region. The explanation, or one of the explanations for this, is that in this particular magnetic field configuration, you have this very strong magnetic field of negative polarity here and a very strong positive polarity on the other side, basically caging the polarity inversion line with the reconnection occurs. And this magnetic cage is actually preventing the plasma from leaving. So you're suppressing the plasma motion by this very strong magnetic field of few kilogauss in magnitude. The light is able to escape, but the plasma is not. So in principle, as I already showed you, that stellar observations are already telling us that the large-scale field of these stars, the large-scale magnetic field, is much stronger than the solar one. So perhaps this large-scale field can provide the required confinement conditions that would explain and would solve this problem with extending the CME activity to stars. And of course, if you look at dynamo simulations for guidance, those dynamo simulations will also tell you that fully convective stars, like the ones that are here in this region of the diagram, will host magnetic fields that can reach several kilogauss in magnitude locally, but also globally. So those types of magnetic field strengths are probably enough to provide the required suppression conditions. So we decided to test this using three-dimensional coronal mass ejection simulation using flux rock erosion models. And for this, we're basically going to use a twisted cluster starting from one of our Alphen wave solar stellar simulations. So the interesting thing about this model is, again, as typically we try to do, is this model has been tried to validate against solar CME observations. This is a study by Mang Jing and collaborators, and this is from their paper, and this is a press release out of that paper, basically comparing a little bit what the model predicts in terms of coronagraph images against some solar satellite observations of the same event. So we decided to take the parameters of this calibration study, which is very well understood, but we applied it to a more younger sun, in the sense of we artificially increase the main dipole field of the sun by a factor of getting it out to 75. The original one from the sun is on the order of 2 to 3 Gauss maybe. So we increased it by a few factors just to make it a little bit stronger. And then, of course, we run a series of numerical simulations. We follow them in time, and we try to characterize all of them. So indeed, we were able to confine coronal mass ejection. So this example shows an eruption that would have an equivalent amount of reconnected flux comparable to a X-class flare of 5, X5 in the GOES classification. As you can see here, the plasma is restricted to basically stay within the low corona and is not able to go. This, and this is basically what I just said. The same coronal mass ejection erupting on the sun will look something like this, and it will generate a very big transient in the CME with a 2,000 to 3,000 kilometers per second speed. I encourage you, if you're interested, you can also look at this recent paper where they actually also look at this problem of the suppression or with the presence of a large scale field, how it basically affects some of the instabilities that are required to make coronal mass ejections happening. So you can actually see it in this paper. So some of our results also indicate that both the mass and the CME speed. So we have here the different simulations. The confined ones are the red points, and the escaping coronal mass ejections are the blue ones. As you can see here, this is a relation between mass, and this is just a number that is quantifying how strong the eruption is, and there is some sort of equivalence to put it in terms of the flare observables, but this is, of course, very tricky to do. So if you want the details, you should read our publication. I'm also including here 2 historical solar events, the famous Carrington event, and another event, 775 AD event discovering 3 rings. As you can see here, the masses of the eruptions are not so much affected. However, against observational relations that you can try to measure for the sun. And the same here we have for the CME speed, but all of our events show speeds that are significantly decreased with respect to the expectation for solar events. So the large-scale magnetic field slow down all the CMEs, and this, of course, makes them much less energetic than expected. So these predictions, and this is an interesting thing, that these predictions are actually consistent to what the very few information we have for stellar CME so far, which is what I'm going to show you here. So until very recently, there were no definitive detection of stellar CMEs, which is actually puzzling, right? Because in principle, you see all this flaring activity from stars, and people have been looking for CME activity, but so far there has been no luck. This is just some of the publications that have tried to look very carefully for them, and they haven't been able to find them. There's a paper by Sofia Moshko and collaborators trying to show a compilation of historical stellar CME candidates, which is where I'm taking these plots from. This is again showing CME mass and CME kinetic energy. And you have all the gray points here are the solar values, basically, that I showed before. And the red line is a fit to this, again, to these points and extrapolation. And you have some other equivalences for the dashed line. For instance, this is parity between the flare energy and the kinetic energy of the CME. You can see here in green all the points that correspond to stars. And in colors, you see some historical solar events, very big events, like Hurricane Carrington event and some other events have been reported in the literature. The first thing you notice is, like, of course, like this is big scatter in this relation, and there's orders of magnitude of scatter, but most likely, like the masses of the events are actually not that bad, not that far from the solar extrapolation. However, the kinetic energies are significantly decreased by several orders of magnitude, what you would expect for this type of X-ray energies that we observe in the flares. So Interestingly enough, there were two recent studies, one by Constanza Argirofi using Chandra that actually detected blue shifted coronal emission that was, in principle, interpreted as a coronal mass ejection, and a very recent one by Kosuke Namekata in the young sun-like star AK Draconis. And I'm plotting here the parameters that they derive for those events. And again, the trend is the same. You have similar masses compared to the solar extrapolation, but extremely diminished kinetic energy, which is all consistent to our prediction of the CME suppression scenario. So we have done a lot of this work and we try to move now to the strong and high complexity regime, magnetic field regime, such as the one expected for M dwarfs. So we are taking prediction from dynamo models tailored to these types of stars, and we are using it to drive our flux drop eruption models and try to put this into the background magnetic fields that are actually consistent with observations using polarimetry or just CMAP broadening measurements from a spectroscopy. The idea that we had is to try to explore this CME magnetic confinement spectrum. So this is from a different study in which now we have a single coronal mass ejection erupting, but we are changing the background magnetic field. So sometimes we can have weak confinement by the magnetic field. So you will have just a kind of regular coronal mass ejection blowing out. In a case in which the magnetic field is a little bit stronger, and then the CME is going to have a harder time escaping, but eventually it will do it. It will just get fragmented in the process. So some of the material will remain and some of the material will be able to escape. And in cases in which the confinement is strong enough that pretty much none of the material escapes, and this is a fully confined coronal mass ejection event. And the idea is to evaluate how the corona of the star looks like across these different scenarios. So I'm going to go quickly here because I'm running out of time. So I'm going to show here the weak CME confinement scenario. And here are just basically showing you some of the capabilities of the space weather modeling framework. So I'm showing you here synthetic images that are emulating the response channel that we usually use to observe the sun, like different channels of the AIA instrument of different wavelengths of the extreme ultraviolet, and also some X-ray contours that are emulating the response functions from one X-ray solar telescope, I think is Hinode. So as you can see here, we have in this case, like this darkening of some regions, which is going to be associated with these dimming features that we sometimes observe in coronal mass ejections on the sun. But interestingly enough, this type of weakly confined CME event generates this flare-like profile in X-rays that is actually being powered up by magnetic compression of the plasma, not by magnetic reconnection. And this is actually very interesting. This is a prediction that we are doing out of our models, that in principle, we should observe a lot of this flare-like activity in stars that have some sort of suppression of CMEs going on. And of course, you see here the different light curves and how the different light profiles evolve as a function of time. And in the bottom panels, what I'm showing you here is the expected Doppler shift signatures that we should be seeing in some of these lines. So I'm going to skip these two slides just because I'm going to be close to the 45 minutes. But if you have any more questions about the other events, I can tell you. I just want to finalize here with a little bit on the type 2 radio bursts, because these are in principle another way of trying to detect coronal mass ejections. They are indicative of an MHD shock that is taking place because the CME is moving faster than the local Alpen speed. It's a normal shock condition, but in this case, for a magnetized medium, the speed of reference is the Alpen speed. So they have a very strong connection with solar energetic particle events. And typically they look something like this, just a frequency drift in a radio spectrum, basically from high to low frequencies, and showing lighting up the fundamental and the harmonic plasma frequencies. Again, what I said before, this is interesting because this is expected to happen when the coronal mass ejection speed is larger than the local Alpen speed, basically. And this is what I'm showing you here. This is a map of the Alpen speed in the plane of the sky for the sun. And this is just an example of a CME taken out of this paper, which they trace the speed of the CME and the appearance of the type 2 burst. And basically, it's basically happening when the CME becomes super alpenic. Interestingly enough, the statistic of the sun indicates that these shocks and this emission comes relatively close to the sun. Relatively close is on the order of few stellar radii, very close, 1.5 to 2.5 stellar radii of height, basically. And this is important because the frequency of the type 2 radio burst and its intensity too is a function of the ambient density. So the closer you are to the star, basically the higher the frequency is going to be, and also it's going to be stronger the emission. However, I already told you that due to magnetic suppression, stellar CMEs are slower. So this means that they become superalbenic much farther out from the star. And this is two examples that I show you from some of our M-dwarf simulations, showing you here a weakly confined CME, a very more strongly confined CME. And this is comparing the alpha speed profile against the radial speed profile of the CME. And the CME in this case, for instance, is only becoming superalbenic after 10 stellar radii of height. And what this means is that the radio frequency associated with this emission, this is our shock tracing algorithm here, showing where the shock is expected to come from. The emission associated with this type 2 type of emission is going to be shifted to very low frequencies. And actually what we found in this paper is that they're so low, they're actually getting very close to the observational limit imposed by the ionosphere of the Earth. So they become extremely challenging to be detected from ground-based observations. So this might also provide an answer of why all these dedicated campaigns observing radio, they have not been able to find a type 2 radio burst in other stars, because it's going to be much harder because of these confinement conditions. So I don't have enough time. I think I'm running out of time, but I'm just going to leave you with this particular slide, which is advertising a little bit our most recent work, which has been trying to investigate the space weather in this famous AU-MIX system. AU-MIX is a very famous star, has been observed multiple times as a very beautiful debris disk. They're resolved by HST observation, but very, very interestingly, very recently, 2 transiting Neptune-sized planets were discovered. And because this star is very young, these planets are actually prime targets for trying to study this process of the atmospheric escape, the erosion by the activity and stellar wind and high energy emission from the host star, because this particular star is extremely active. You can see here the NASA poster of this particular discovery paper, that these poor planets are going to be embedded in these flares of fury out of AU-MIX, which is actually a very interesting flare star. The flare star has extremely energetic flares and very frequent ones. So we decided to try to carry out a comprehensive study of the space weathers of the system, simulated the stellar wind and the connection between flares and CME, simulating some super coronal mass ejection in this event, and tried to characterize, in principle, the atmospheric loss from some of these exoplanets, and in the most recent study, to link some of the CME activity with energetic particles that might be injected in the system, and how they might reach the exoplanet orbits, what will be the fluxes, and so on and so forth. So I'm leaving you here the references. All these papers have been either published or accepted, but you can find all of them in ADS on the archive. I will finalize here. I will leave here my concluding remarks, and I would just say that nowadays it's possible to try to study the properties of magnetic fields in other stars that are not the sun. And the wide parameter space that the stellar astrophysics offers is fundamental to try to understand actually how everything works. Of course, solar observations are never going to be challenged by any of the stellar observations in terms of completeness, quality, temporal or spatial resolution. However, you cannot change the parameter space of the sun. It's just the sun is fixed. So you want to see how the parameters change and how they affect things. You need to look at the stars. If you want to study activity, and in any context, either for radial velocity characterization or atmospheric characterization of exoplanet and how activity influences those measurements, you need also some knowledge of the magnetic field, because the magnetic field is actually the driver of this activity. So again, in the context of exoplanet atmospheric characterization, the space weather needs to be taken into account, because these planets are not evolving in vacuum. Of course, you have all the coronal activity, stellar winds, flares, coronal mass ejections, and so on and so forth. We have also been pushing out this magnetic suppression scenario as a viable mechanism to solve these problems that we have with the flare CME association. And so far, everything is consistent to what we predicted back in 2018. And this has very strong consequences for the expected signatures and detection of these events, for instance, in the case of radio quiet scenes. We have extended this mechanism for M-dwarfs, and things seem to be working. And of course, this has critical effects to these very close-in exoplanets around these low-mass stars. And this type of CME confinement, our simulations predict that it's going to induce a lot of activity in the corona that should be in principle observable with a next generation high-energy astrophysical instrument. So I think that would be all, and sorry for the 5-minute extra time, but thank you very much for your attention. I would be happy to take any questions
Thank you very much, Julian. Very nice, interesting, and also interdisciplinary talk. So now the talk is open for a question, and Miguel Perez Torres, please, you can manage the questions.
Okay, so thanks a lot, Julian. Very nice talk, very comprehensive, and yeah, I'm sure the audience will have questions. So let me just check. No, I don't see any hands raised so far. Let me just warm up question. And most of these flares are accompanied by coronal mass ejection, but sometimes that's not the case. And I'm wondering, is there observationally, I mean, beyond what you showed, somehow, I mean, we are, or I in particular, I'm interested in the radio observations that could maybe tell apart what is a flare from a CME or maybe other phenomena. So is this anything that, I mean, how do you, from observations, can maybe exclude, or can you try to exclude what is a flare not accompanied by a CME, or just the other way around, maybe a confirmation that this is a CME?
So this is a good question in the sense of, unfortunately, the situation in the radio regime so far has been that so I would say that, and probably the solar physicists in the audience might correct me if I'm wrong, but from the different types of radioactivity observed in the sun, only type 2 radio bursts you can typically associate unequivocally, to some extent, to CME activity. There are other types of radio bursts that we observe, like type 3s or type 4 and so on, but a lot of those might also be associated with the flares in the flare side, or some coronal other processes, but not with this escape of plasma in the form of a magnetized cloud that is moving very fast and is shocking the material in front of it, right? So in stars, people have looked for very flare active stars. So this type of flare stars that I've seen to flare a lot, either in optical wavelengths or in X-rays. This type of flaring stars, like they are very well known for many years. So people have tried to point the radio telescopes at them, but so far none of those campaigns has been able to detect any type 2 radio burst. So to distinguish them, I think the first step would be to try to actually detect something. I think there was a nice detection by the type 4 radio burst out of Proxima Centauri by a team from Australia. Yes, that's right. But again, this is a type 4 radio burst, so it actually is related with all these processes that are occurring there. But for instance, out of that, there is no direct link you can do with a CME parameter, right? While, for instance, with the type 2 radio burst, the frequency drift, you know this very well, but the frequency drift is telling you immediately, more or less, the speed in which the perturbation is traveling. So I think type 2 radiovers has been this kind of very long sought after signature, but so far they haven't been observed. And now people have tried a lot of things, like looking for Doppler shifts in some of the Balmer lines, for instance, in which you would expect to see this filament eruption. This is actually how the study by Kosuke Namekata did it for A-Cat Draconis. So again, if you look at that plot, depending who you ask, some people will be convinced by some of those candidates and some they will not. so far the situation in terms of the observations is extremely challenging. And of course, there's always the question, is it because we are lacking the proper instruments or the proper techniques to observe them, or is it because there's something more physical behind it, right? And this is what we are thinking that is happening, that all of these are signatures that the conditions around those stars, because the large-scale magnetic fields are so strong, are not the same, are not as comparable as we observe them in the sun. The problem with the sun is that the small-scale structure are at least 3 orders of magnitude stronger in magnetic field than the large-scale structure. So small-scale structure thing dominate. But in M dwarfs, you see that this organization, at least dynamo models predict this organization of small-scale field turn out to generate this very strong dipolar field of few kilogauss of magnitude. And that is actually enough to suppress a lot of the CME activity. In our study, just by increasing the magnetic field of the sun, the polar magnetic field, to 75 Gauss, that was enough to basically suppress all the CME activity from the sun up to flares on the order of X10 or so, at least using the numerical models we are using. So, a kilogauss field should be able to stop a lot of this CME activity, and that might explain basically why it's so difficult for us to observe it.
Yeah, thanks a lot for the clarification. In fact, I had, well, let me just check. Still no questions. Well, so I will, with the permission from the audience, anytime, please just raise your hand here, and so I can see and I can give you the word. But otherwise, I wanted actually to continue on this point you raised up, Julian, the fact that the high magnetic fields may actually prevent, or well, you showed this very nicely, can explain why we are not observing these type 2 bursts, and at least in radio. So I'm wondering, this still doesn't prevent, of course, to have this very large flare activity that should be observable, again, maybe not in radio, but at other wavelengths, right? Mm-hmm. So which is then maybe here again, I mean, we are having some kind of a hard time from the radio perspective to convince some side that, well, maybe what you are looking at in some cases like Proxima is due to star-planet interaction rather than just, flaring activity. And maybe but of course Proxima is not, it hasn't this tremendously huge more than kilogauss magnetic field, but still, it can range from 200 to 600. So I wonder, well, maybe this could also prevent the appearance of CMEs. That could be one problem less in terms of misunderstanding whether we are dealing with a star-planet interaction from the radiation we see. But of course, if we're gonna still have a lot of flares that are not related to star-planet interaction, that of course is an issue we have to handle. So, is there any suggestion again from your side? Maybe I know campaigns that are also simultaneous at other wavelengths. You show a very nice figure where you show that many of these flares were accompanied by a coronal mass ejection, but one of them didn't have this coronal mass ejection. So how
was the other way around? So
where's the other way around? Sorry.
Yes.
So
all the flares that I show were they had no coronal mass ejection,
CME except
but only that one, exactly. So, and this is actually a very good example of, in principle, this mechanism in principle already working on the sun. It's just that in the sun, the way we think is happening is because of the same small scale structure. It just happened to have like this particular dipolar, very strong dipolar field, this active region, that is the one that is in principle generating this suppression. But for stars, we think that the large scale dipole might be enough to do it. So of course, you're going to have perhaps similar type of small scale structures in terms of active regions, perhaps with higher filling factors in other stars, so many more active regions over the surface of the star. But the large scale magnetic field might be strong enough that we don't really need to know the details of that small scale structure, because we cannot observe it in stars. What we can get some handle on is this large scale structure through Zeeman Doppler imaging and spectropolarimetry. But those magnetic field values are already large enough to provide some sort of what we would need. And of course, because it's the main dipolar field of the entire star as a whole, this is actually the field component that survives the most in distance, because all the other components decay faster. The dipole is the one that decays slower. So this is the one that is going to matter the most. So as long as the dipole field is strong, there's probably going to be strong suppression. In some of our recent works, we're also seeing that there's a lot more going on here. Like everything I've said is kind of associated with a dipole field, which is aligned with the rotation axis of the star, which you could think is okay, it's a good approximation. But in many stars, we see misalignments between these fields. So those cases will introduce additional degrees of freedom, in which perhaps we've seen that in some of our simulations. The same coronal mass ejection is suppressed in a given magnetic field configuration, but if you just tilt the magnetic field a little bit, you might be able to actually get the CME to escape. But of course, all these type of studies require a lot of numerical simulation time, and they're very time consuming to do. So a lot of this has been, still under development, let's say. In terms of your question for the observation, I think the way to go is this multi-wavelength observations is the only way to try to convince yourself that whatever signature you're seeing is not being introduced by any some sort of other artifact and whatnot. One thing that we actually saw in the AUMIC paper that I recently published, but I didn't have the time to talk here, is that there are recent claims of people, as you said, that are trying to detect this radio emission that is in principle going to be associated with this electron, cyclotron, maser radiation from star-planet interactions, in which basically you have this Io Jupiter equivalent to other systems to some extent. So the interesting thing about that is, in order for this mechanism to work, the planet needs to be within a subalbenic domain, right? So this is in principle the condition for this to happen. But one interesting thing we saw is that when you have a coronal mass ejection that arrives to a planet that is in that condition, it actually changes the local condition temporarily to a superalbenic regime, because the CME is moving so fast, it's carrying so much dense material that the local alpine speed at the planet orbit changes. So if, now this is a big if, because all of this is theoretical, but if this system is generating this star-planet interaction in radio and a CME arrives, the radio signature is going to disappear. It's actually generate a dimming in radio, which is counterintuitive because you always think like, well, the CME arrives and then you light up in radio, everything. But in this case, because it's basically shutting down this connection between magnetic field lines between the star and the planet, this type of emission will be shut off, and we will in principle see a dimming of this radio star-planet interaction emission. Again, the both things that I'm talking here are extremely exciting, but unfortunately, none of them have yet been detected like with clarity, right? Neither the star-planet interaction emission, there were some claims back in Cursor, some, in principle, tentative first detection, but I don't know, I'm not very convinced. And the CME part either. So again, it's just we are in a regime right now in which models are actually telling us a lot what we could or could not perhaps see, but observations are the ones that probably need to find very clever ways to try to measure these things. Yeah.
Okay, thank you very much for this for this explanation. Yeah, and so I don't see that there are any other questions, and you know, I could go on and on, but I think I also chat a bit with you when we met in Toulouse. So you know, a number of questions were already faced by them. So I look forward to meeting you. I think next October 18th.
Yes, I will try my best to attend in person. It would be absolutely great.
This Ochoa meeting will be nice, and I think it will be plenty of time to talk and maybe to enjoy a beer together. That would be nice.
Okay. Sure
so I know from my side, I mean, I don't see anyone else asking. I told you, Julian, the 1st of September is a bit.
That's
tough.
okay. It's okay. We can talk more during my in-person visit, of course.
Yeah. So I'll give the word. I know if Isabel or the director and John, if he's around, he wants to give to tell something. René.
Yeah. Seems there is no more questions, so I think we can close the talk. And thank you again, Julian, for this wonderful talk, and I enjoy a lot.
Thanks to you for the invitation.
Hope to see you here in October.
Yes, absolutely. I will try my best. Absolutely.
Yeah. Bye then, Julian.
All right. Thank you, everyone, and thanks a lot for the invitation again. Ciao.
Ciao.